Next up, we have condition variables. So remember, we're in concurrency in the blue part of the course. So we looked at multi-threading and the thread API. We saw how to use locks, and we also saw how to use locked data structures. And now we are in essentially chapter 30, condition variables. So remember that we use multi-threading because it makes things faster. Concurrency, by using concurrency, we increase the speed of execution, we reduce time we need to execute a program. However, this gives us critical sections in our code, and then we have to fix that, and the fix is using locks. However, so even though locks work, they slow down a program, and if you have a lot of contention for locking, that might result in making our code slower, unfortunately. So along with locks, so locks do solve problems, but sometimes we need something else. So we want a thread, let's say we have two threads, child 1 and child 2, and we want to execute code in many steps, and we want child 1 to execute some crucial step. This could be a critical section or not. Maybe it's just getting something from a file. And then it wants to let's say it wants to indicate to another sibling child, child 2, that this thread is done. So something over here was completed, and this child wants to send a signal to a thread, child 2, that is waiting for child 1 to do its step 1. So child 1, let's say, cannot proceed until child 1 is at least done with part of its job. So once child 1 completes this job, this one step, it can somehow magically let child 2 know, and then child 2 can continue, and child 1 can also continue with whatever it's doing. Okay. So this is one way to do it, and this will actually work if all you have is one child 1 thread and one child 2 thread. This might actually, no, this is probably just about work. However, programmers make the mistake of doing this even in cases when you have multiple threads executing this child 1 code, multiple threads executing child 2 code, and you have things like this condition, done condition, flipping back and forth between 0 and 1. Under those kinds of situations, this setup will just not work. It is pretty much, it's probably a good, it's a good bet that this will work if you have just one thread executing child 1, just one thread executing child 2, and then done is initialized globally to 0. So we assume that this done is in the parent address space, the global variable, that can be accessed by both child threads, child 1 and child 2. So that's not shown here, but that's the assumption. And so both threads can see this global variable, it's shared memory, and it's only going to change from 0 to 1, and that's it. It's never going to change back. Under all of those conditions, yeah, you could probably write code like this. But the mistake that a lot of programmers make as well is they think that if you can do this, then you can do much more with this signaling variable done. So the idea here is done is initially set to 0, and so if child 1 ends up executing first, it checks the value of done. If it's equal to 0, remember this is doing nothing, staying in the loop, spinning. So this is a spin, not a spin lock, but it's spinning, waiting for child 1 to be done with its first step. And while this is waiting, child 1 can come along and eventually finish step 1, set this variable to 1, and this will get out of the loop and go on to its next step. So it does make sense, right? It'll probably work. There's only one thread in this case, let's say, only one thread executing this child 1 code, and it's only going from 0 to 1. It's never going to flip back, so there's nothing in here that'll change done back to 0. And this is not in a loop or anything like that. Under those circumstances, yeah, this will probably be fine. But as a general solution for signaling, and we will look at this is just it's like a nice simple case of sending a signal from one thread to another thread. So we'll use this simple situation, but keep in mind that this can be it can be much more complicated. You can have all of these steps in a loop. You can have these conditions go from, like, say, from 0 to 1 to 2 to 3 and so on, and then maybe back to 0 in general. We're not going to do that. Here, we're going to take the simplest possible case and then try to come up with the best technique to do what's called changes in conditions. Okay, so this done variable can be used by child 1 and child 2. For child 1 to send a signal, that's what it's called. So you're sending a signal indicating that child 1 is done with something and child 2 is waiting for that signal. It works, but it is inefficient in that child 2 is set up to spin. It's doing this infinite loop thing. It's not infinite. It's an infinite loop if there's nothing to change it. If there's no thread that's going to change done, then it is an infinite loop. As long as there's at least one thread that's going to change done to 1, then chances are you're going to get out of this loop. However, even if that is true, even if child 2 is able to get out of that while loop, it is spinning, and so it's using 100% of the CPU while it's waiting for some other thread to change that done variable. A better approach certainly would be to use the sleep function to have the child say, all right, it's not happening right now, let's just wait and see what happens later. And then child 1 may come along and finish that setting of done to 1. So here's the crux of the problem. How do we wait for a condition to change? In our case, in this example that we just looked at, the condition was having done, the variable done becoming 1. So that's the signal. So how can we have a thread wait for this condition? So the condition, once again, is change of the variable done from 0 to 1. So this condition or this change will happen under the control of some other thread, and in one thread you're waiting, in another thread is what's going to change that variable. So we looked at a very simple situation so that we can understand the problem and so on, but just keep in mind that there may be many threads waiting for that action, and there may be many threads potentially changing or signaling. And so we want to keep that in mind. And how can we do this without using a spin wait? Spin waits do work, but they eat CPU cycles. So spinning is something that CPU can do really fast, but it hogs the CPU. On a single core machine, you are eating a lot of CPU time and thereby slowing down the possibility that some other thread can be scheduled and change that done variable. So if it's just a single core, or if, let's say, a bunch of threads that rely on some other thread to change something are all running on the same core, then you are slowing down the thread that can change things. So that's the one that we're waiting for, and so we're slowing down the program as a whole. So that's why we want to avoid spinning. Spinning does work, but it's not a good thing. Okay. The solution to all of this, it turns out, is to use what's called condition variables. And it turns out that you can use condition variables to do the same kinds of things as lock, but the way we will look at condition variables, we will see pretty soon that it does different things. The condition variable is essentially just a change in a condition, and you want along with that condition, You want a variable that has a queue where threads can put themselves to wait for that condition to change. So not only do you have that done variable, but you also have a queue that threads can wait in. And so just like with the lock, when you lock, you think of that as a variable, but really the best way to implement it is to use a queue so that as soon as you unlock, as soon as when you try to lock and it is already locked, what you want to do is you don't want to spin. You want to wait on that lock to become available, and so you put yourself in a queue so that your thread doesn't starve. You want the same kind of thing here with condition variables. Okay, so you have a variable. Let's just say it's an int, and there's a queue involved, and you can, when you call the wait function, that's what we'll have here. You will end up going to sleep, and you get put on a queue so that eventually you do get woken up when there is some thread that does what's called a signal. So some other thread should be able to change the condition and wake one or more threads that are already waiting, and that's called signaling. Okay, so there's two operations, just like lock and unlock. This is sort of analogous, but not exactly the same. You wait, that is, it's sort of analogous to locking, and signaling is similar, but not exactly the same as unlock. This is much more, it's meant to be much more direct.